Hello everyone. Are you ready? Good. Let's start. So here's a picture. One of those pictures you should look at all the time. Okay. So these are some Fourier transform pairs that we discussed. Or if we did not, it was in a homework set, and I'm sure you're doing that already, right? Okay. So what is the first pair? What does the function on the left look like? It looks like the sink. So on purpose, I did not label the axes and I did not put any particular values because we can scale them as we wish, right? But I'm going to write one particular set of values for them that work, and everything else can be derived from those using the usual scaling properties, right? So if I take sink without anything else in it, what are the cutoff frequencies in the pulse that we get as its Fourier transform? So the exam is coming. I mean, no relation to the question, but in the exam, I'll let you have a cheat sheet, right? And of course, you don't want 10 pages of cheat sheets. I'm not going to allow that anyway. One page, two-sided is okay, but usual letter size, okay? And no magnifiers. So obviously, you don't want to fill it with all kinds of things that can be derived from each other, right? So, you know, this would be a good candidate for your cheat sheet, right? So if you know, what sink goes with, and if you put on the side the scaling property, everything else you can get from there, right? You're not going to write these pairs for every possibility. Anyhow, back to the question. What are the cutoff frequencies? Pi and negative pi. Thank you. And the amplitude is 1. Okay. All right. This is the second pair. Is sort of a dual to that. Again, it's not marked. So if I choose this to be negative 1/2 and 1/2, turns out what I get is going to be sink on the other hand, but not a sink by itself, sink omega by 2 pi, right? Again, if the width of this pulse is different than 1, you can scale the Fourier transform according to our scaling properties. Furthermore, if this Fourier transform, if the pulse is not centered at 0, which it is right now, right? It goes from negative 1/2 to 1/2, right? What if it started at 0 and ended at 1? What would you do then? You would use the time shift property, right? So the Fourier transform would look identical, except it would be multiplied by e to the negative j omega times the amount of time shift, which changes the phase of the Fourier transform. But the magnitude will be unchanged, right? So, and the amplitude here was 1. So this is a triangle, and it's a triangle that can be written as a convolution of the two things of this pulse at the top with itself. So the convolution will double the width because, when you're convolving two functions of finite width, the widths add up in the convolution. So it was 1, now it's going to be 2. It's going to start at negative 1. That was an example, so I'm just reminding you. So what I'm looking at now, the triangle can be written as a convolution of the two pulses. Therefore, the Fourier transform just gets squared, right? That's the convolution property. So sink omega by 2 pi squared, all right? And you see what happens to the octopus when you square it. First of all, the negative values disappear, obviously, because it's square. So the parts that were on the negative side flip up. The other property is that because we are scaling it so much slimmer and sharper, right? It dies off so much more quickly. And that is consistent with our intuition that if the signal in time is smoother, it doesn't have sharp edges like the pulse, then it should not have too many high frequencies in its spectrum. And you can see this comparing the second and third pairs. The pulse has very sharp edges, therefore it has high frequencies present, whereas the triangle is smoother, therefore the high frequencies die down faster. All right? So the example on the left is e to the negative t. Okay? So you did this in the discussion on Friday, and you found that I think there was a factor of a, but those can all be derived by the scaling property. So for that you would get 2 omega squared plus 1. All right? I'm putting this symmetric version of the exponential. We had this one-sided exponential, but of course, because it's not symmetric, it gives us a complex valued transform. To make things look pretty, I'm only using symmetric signals in time so that the Fourier transforms are real valued. Okay? So that's why instead of e to the negative at, I'm giving you a nice and two-sided symmetric exponentially decaying function. And finally, the last one is a homework problem. So if the one on the left is a Gaussian function. Let's say e to the negative t squared. Again, I did not put numbers, so it could be scaled to anything. And the one on the right, you will show in your homework. This is, by the way, a very easy homework problem. But anyway, just so you do it once in your life, I put it there. So it can be written as the Fourier transform is also a Gaussian with different coefficients. Okay? And those coefficients you'll find in the homework set, right? If you haven't done already. All right? So it's kind of interesting that the Gaussian functions look still Gaussian when you take their Fourier transforms. That's an interesting property. All right. So, any questions? You remember all of this? Feel happy, confident? Okay. So, again, make sure to look at this, and you should know these pairs. Okay, they are famous pairs and power couples. So, keep them in mind. Now, let me go to my notebook for this class. I don't want good notes 5. Okay, so we kind of haphazardly define Fourier transforms in this form and never asked the obvious questions. When you integrate something from negative infinity to infinity, how do you even know that exists, right? Is what you're integrating really integrable? So we kind of postponed these questions until today. This is the moment of reckoning, so we have to address some of these issues. I will start very simple. I'll give you a sufficient condition on x that makes this integral well defined. Okay? Sufficient means it's just sufficient. If you have that property, it works. If you fail that property, that doesn't necessarily mean it does not converge. If that were the case, I would have called it necessary and sufficient, right? So a simple sufficient condition for existence of x omega. So we kind of jumped we jumped the gun here. I even already wrote x of omega, not even knowing if the right-hand side makes sense or not, right? So far we were a little loose with this. But now today we'll add some amount of rigor, although full rigor will not be possible within this course. So what is a simple sufficient condition? Here's a theorem that you can state. The condition I'm going to give is sufficient. Being sufficient and not necessarily, it's actually a little conservative, right? So you will have signals x satisfying this, not satisfying this condition, still having well-defined Fourier transforms. Okay, so conservative in that sense. And because it's conservative, it's going to also give us some properties for the Fourier transform that we didn't even ask for, such as continuity and stuff, right? So the theorem states all of these in one shot. The condition is absolute integrability of x, which means the integral of the absolute value of x of t dt exists, converges to a number. So we will succinctly write this as less than infinity, okay? If that notation is not too offensive to you. Then x omega exists, right? And some things we didn't ask for, but come for free because this is a somewhat restrictive condition, more than necessary. And continuous. I never asked for continuity, but it comes for free. I'll take it. And continuous, right? In addition, you can also show that x omega goes to 0 as omega goes to either positive or negative infinity. Okay? Again, this part is bonus. I never asked for those. I get them because I'm using a somewhat conservative condition. Okay? All right, so I'm not going to prove much. In fact, I'm not even going to get into the continuity and the limit being 0 properties. But just a little note. So the main argument here is that if I'm given a function f of t, and if its absolute value converges, the integral of the absolute value converges, then f of t dt, if this is less than infinity, then this is also less than infinity. Okay? You can just take the absolute value of this and argue from that. Okay, so I'm not going to go into the details of this. But basically that's what's happening here, because the thing that I'm really integrating is this, right? X of t e to the negative j omega t. What is the absolute value of x of t e to the negative j omega t? It is the absolute value of x multiplied with the absolute value of e to the negative j omega t, and I know this is 1. So this is really nothing but the absolute value of x. So the condition we asked for, the absolute integrability of x, amounts to being this. Okay? And what we get as a result is this. Okay? So that's the main idea in the convergence proof. I will not say more, just take it as a fact. That's good enough for me. All right? But let's go back and check the examples, the 5 pairs of Fourier transforms. Okay? Let's see. Oh, they weren't here. Where are they? They are here. Okay. So I'm going to number them. 1, 2, 3, 4, 5. Look at 2 first. Is it absolutely integrable? Yes, obviously. It's finite duration. I can integrate it, of course. And you can see the Fourier transform obviously is well defined. It's a sinc function. It, in addition, is continuous, right? And the tails converge to 0, which are the statements of the theorem. If I look at 3, again, it's a finite duration signal. I can integrate it from negative infinity to infinity. It's the same as integrating from negative 1 to 1. So that exists. It's absolutely integrable. And sinc squared itself satisfies all the properties, continuity and convergence to 0 as omega goes to infinity. Same thing with an exponential function. The integral of an exponentially decaying function does exist. Even if it's two-sided, individual both sides exist. So the absolute integrability condition holds, and we get a well-defined continuous function Fourier transform that converges to 0 as omega goes to infinity. Same thing for the Gaussian. If you took probability, Gaussians are used as probability distributions, and their integrals, upon some scaling, gives you 1, not for this. You would need a square root of pi somewhere, and then you would need to divide the argument by 2. But anyway, so up to some scaling, we know that the integral is 1. So in a general function like this, we know that the integral at least exists, if not 1, right? Therefore, the theorem is again applicable, gives us a nice and smooth continuous function that goes to 0, right? All clear? But look at example 1. Do you think that's absolutely integrable? Those who say no, can you argue why? And let me assure you that you can't just look at sinc and say, of course it's not integrable, because that's a non-trivial integral you would have to evaluate. Any ideas? Say that again, louder. No, not you, the one. Sorry, your friend is better. Yes, so the theorem said if x is absolutely integrable, the Fourier transform exists, blah, 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 but also it's continuous, right? If this was integrable, I would have seen a continuous Fourier transform, which I don't. It has a jump discontinuity. So that alone, the theorem alone, is enough to conclude that this is not integrable. There are other arguments more complicated to show that it's not absolutely integrable, but that's enough. Okay? But there you go. There is a Fourier transform. So what's going on here? Well, the theorem was only sufficient, right? Absolute integrability is by no means a necessary condition for the existence of the Fourier transform, as this example demonstrates. All right? So it's good to know that. And knowing that, now we'll go a little further than this. So what about, okay, so we have this absolute integrability condition that assures us that the Fourier transform is well-defined, right? And then it can be relaxed also. The sinc function showed us that. But there are a number of functions that I'm really interested in for which I know that this integral in the Fourier transform does not really exist. For one thing, I can give you x of t equals 1, right? Will that transform exist? What you're integrating never dies off, so there is no way that that integral will converge, right? Also, if I give you, sine omega naught t at some frequency or cosine omega naught t, you're not going to get convergence of the integral. So these are important functions, and it's kind of sad that we don't have a Fourier transform that exists for them. Okay? And note, I'm not talking about the sufficient condition. Okay? Sufficient condition works for some functions, fails for some others, but sinc doesn't satisfy it, but it still has a Fourier transform. I'm talking about functions where without even thinking about that condition, you can argue directly that the Fourier integral at the top does not exist, period. Okay? So it doesn't have a well-defined Fourier transform. Don't have Fourier transforms in the strict sense. But fortunately, there is a non-strict sense of Fourier transform. There is a notion of a generalized Fourier transform that does not require this integral to converge. And using that, we can actually talk about Fourier transforms, not in the strict sense, but in the generalized sense, of these functions that I just mentioned. Okay? The theory for this generalization is based on the theory of distributions. I'm going to go into it a little bit, just to give you a little flavor, and I'm not going to hold you responsible for that or anything like that, but it's good to see a little bit of what's going on in the theory of distributions a little bit. But for now, hold off on that. And using the properties of the Dirac delta function, which we call the unit impulse, right? Some of the properties which themselves are a little shaky when you don't use the theory of distributions, we can actually justify some Fourier transform pairs for functions like this, 1 sine omega naught t, cosine omega naught t, okay? So for now, I will do sort of a wishy-washy argument for these pairs, and then I will give you a glimpse of the distributions that make those things rigorous. At least that way, when you're doing wishy-washy things, you know that there's actually a firm theory that can justify those things, okay? So, let's start. I claim, and we'll see why in a second, or we'll sort of justify, that the function x of t equal to 1 for all t, for which the Fourier transform does not exist in the strict sense, in the generalized sense, has a Fourier transform which is x omega 2 pi, just a factor, not important. The important part is delta. Here it comes. Delta of omega. Okay? Why? Again, the full answer will never be given. I'll only give you a little sense of that. But a sort of a justification will follow from the synthesis equation that we discussed earlier. Remember the synthesis equation? It said x of t, you can recover from x of omega using this integral. Okay, so x omega e to the j omega t d omega, right? So if I substitute what I just claimed here in place of x, I will get 1 over 2 pi integral 2 pi delta of omega e to the j omega t d omega. All right? 2 pi's cancel. And what can you tell me about delta omega times e to the j omega t integral? Remember this property of delta function. Again, I'll be honest with you in a few minutes and tell you that's not really a function, but anyway, for now let's pretend it is. Delta had this property, this pretend property, that if I multiply f of t with delta of t and integrate it, what comes out is f of remember what delta looks like. It's just 0 everywhere, right? No value of f will matter other than t equal to 0, right? And somehow it has an area of 1 underneath, right? So it will actually spit out f0. So that's one of the fundamental properties of delta that we discussed, okay? So if I apply it here, the integration is now over omega. So I'm going to substitute omega equals 0 in here, right? And that will give me e to the j omega t when omega is 0, and that is 1. Okay? So that's sort of a justification for this Fourier transform pair. All right? Any objections to this? You can buy it. Okay? There's actually a dual to this. If I tell you x of t itself is delta of t itself, okay, x of t delta of t, the generalized Fourier transform for this is x of omega. How do I get it? I just have to integrate x of t, which is delta of t, e to the negative j omega t dt, right? From negative infinity to a positive infinity. So what does that give me? It gives me e to the negative j omega t when t is 0, right? And that is 1. Okay? So, okay, here's what we found. So we found that if x of t is a constant 1, x of omega is an impulse with magnitude 2 pi, centered at omega equals 0. And dual to that is if we have a delta in time, its Fourier transform is 1 for all frequencies. You know, 1 for all frequencies is a remarkable thing. Any Fourier transform of any meaningful physical signal dies off as the frequency goes to infinity, right? A signal who would have equal representation of all frequencies, no matter how large those frequencies are, is hard to imagine. In fact, it turns out to be a delta, which itself is a hard to imagine function, right? So this is a useful pair, and in fact, we can generalize what we just observed here to sinusoidal things as well. So here's the generalization. I told you x of t equals 1 goes with, in the generalized sense, x of omega 2 pi delta of omega, right? So the way we justified this was to apply the synthesis equation to the right-hand side. Now I'm going to ask you a different question. Let's say I tell you the Fourier transform is 2 pi delta of omega minus omega naught, a particular value of a frequency, right? So if I apply the synthesis equation, what do I get? 1 over 2 pi integral 2 pi delta omega minus omega naught e to the j omega t d omega. Again, 2 pi's go away. So what comes out of this integral? It picks the value of this function. The delta picks the value of this function, but the delta is not at 0. It's centered at omega naught, right? So it picks the value of this function when omega is omega naught. So what comes out is e to the j omega naught t. Okay? So x of t e to the j omega naught t. So this is a Fourier transform pair in the generalized sense, right? And in fact, a special case of this, when omega 0 is 0, is what I have at the top, right? Because then x of t becomes 1, and I simply don't shift the delta, right? So the second result is more general. Okay? So that allows us to segue into sinusoidal functions as well, because, for example, if I had cosine omega naught of t, I would use the linearity properties and the usual decomposition of cosine as 1/2 e to the j omega naught t plus 1/2 e to the negative j omega naught t, right? And now I know that this guy goes with 2 pi delta omega minus omega naught, right? And there was a 1/2, so it's only pi, right? Delta omega minus omega naught plus pi. From the second term, I'll get an omega plus pi delta omega plus omega naught. Okay? So that way, you can do something similar to sine. So that way, we can actually define generalized Fourier transforms for sinusoidal things for which the standard Fourier transform would never exist. Okay? And the price we pay for these violations of the classical definition of Fourier transform is that we have to deal with the delta functions. Right? Does that make sense generally? Okay. So now that I can deal with sines and cosines, I can actually deal with any periodic function in time. Because we studied in Fourier series, and we saw that any periodic function can be decomposed into a linear combination of these sinusoidal terms. Right? So now I can define a generalized Fourier transform for periodic signals. I already know that for periodic signals I can use Fourier series, and they look like this. So whatever periodic x of t is, I can decompose it into coefficients a sub k e to the j k omega naught t, potentially using infinitely many of these basis functions, right? So knowing this property here, that didn't work. Anyway, yikes. Okay. So using that property, which I could not box properly, what would you say the generalized Fourier transform is? Linearity. So linearity tells us it's going to be AK times the individual Fourier transforms of these guys. And I know those are 2 pi delta. Oh, where is my K? This is K times omega naught. Okay? Delta omega minus K omega naught. All right? So that way we can also, Fourier series also becomes a Fourier transform in a generalized form of the Fourier transform. Okay? So let me go to the notes to show you a couple of quick things. Where is it? We discussed this. Okay, so cosine, I already discussed that. So if you look at the Fourier transform of a cosine, it's going to look like this. Okay? But we can also talk about the Fourier transform of an impulse train. We will see impulse trains later, but an impulse train is really this. It's like a train of impulses, right? A bunch of impulses that come periodically, every capital T units of time. So this being a periodic function, we can actually technically apply the Fourier series definitions to it. And you can find the Fourier integrating over one period. You find that the Fourier coefficient AK is 1 over T, and it doesn't even depend on K, right? So this is the Fourier series. All Fourier coefficients for an impulse train are equal to 1 over T. And to translate this to a Fourier series, we do what we just did on the notes I was showing you. You multiply everything by 2 pi, and we get AK times these deltas in the frequency. But AKs are all the same, so the deltas all have the same magnitude. They're all worth 2 pi over T, right? So that means, as the Fourier transform of an impulse train, you get another impulse train in the frequency domain, okay? Impulse trains will play an important role later when we talk about sampling, but that will be a while, a couple of weeks at least. So this is yet another example. It's technically periodic, so we apply Fourier series to it, and then apply what we saw just now, this formula saying that the Fourier series can be written as a generalized Fourier transform using the delta functions. All right? All good? Okay. I don't see a lot of enthusiasm today. Is it the weather? Somebody's sleeping in the back. Others are yawning. What's happening? Okay, so I will do something that will not quite wake you up. In fact, it may have the opposite effect. But I'll do it anyway. Okay, I don't care. I'll do it. So I'll tell you a little about distributions. All right? And once a riot erupts, I will stop. Okay. Are you ready? This is not for the faint-hearted, so you need to be awake. It's actually not a big deal. It's really, the genesis of this is people, the mathy types trying to explain, people did these types of Fourier transforms of deltas and stuff, right? There was a guy whose name was Heaviside. I'll tell you about him later in this course. He was an engineer, didn't have any formal mathematical training, but he used all kinds of transforms without calling them transforms, and he used these delta functions left and right, okay? And he used the impulses, sinusoidal things, etc. So he did all these things, and the mathematicians were very skeptical of him. But in the 1950s, some mathy types actually found solid footing for the types of things he was doing, and that's the theory of distributions. Okay, distribution has nothing to do with the distributions, probability distributions you've seen in probability. There is absolutely no probability here. All right. I don't know why they called it distribution. Maybe because they thought about these deltas as some substance distributed in time or space, something like that. I have no clue. Okay, not a good terminology, but we'll stick to it. So let's start by revisiting. I'm not going to talk about distributions yet. Let's talk about revisiting delta, right? How did I define delta, right? I may have used slightly different notation, but we defined a pulse like this that had a width of epsilon and an amplitude of 1 over epsilon, so the area was equal to 1, right? So let me call this G epsilon of t, although I think I did not call it G back then, but doesn't matter, okay? And then we said limit as epsilon goes to 0, G epsilon of t, you find this as delta of t. Okay, so this looks slimmer and slimmer as epsilon goes to 0, but taller, and area somehow remains 1. And the limit of that is delta of t, right? You perhaps bought it, perhaps you didn't, but what does that even mean? So that wouldn't pass muster with a mathematician, right? What am I talking about? Like, this limit is not a function itself, right? So why do I even call it like a function? So that's, I'm confessing my sin, so that was technically a sin, right? And then the other thing we did, one of the essential properties of this delta function was what I just talked about. So we said, delta of t times f of t, if I integrate it from negative infinity to infinity, is going to give us f0, right? I just used this 2 minutes ago and nobody objected, right? So these two things are sort of shady things because delta not being defined, what do I even mean with this integral? Okay? Integrals are things that should be handled with care, preferably using measure theory and stuff, but of course we don't go into that. So these are the two offenses we committed. But before fixing them, we could actually have defined delta using a different function than a pulse. Pulse was easy. Area is 1, of course, right? So it was easy in that sense. But I could have used any g function. So take any function g, with g, with the property that the integral on the area under g is 1. Okay? So one example would be what we already used, something that has amplitude 1 with 1. Okay? Or I can use other things like, for example, the sinc function. Sinc of t. Why does that make the cut? Does it have area equal to 1 underneath? Exam is in a little over a week. So how do I know that? Because I know the Fourier transform of that, right? What is it? Sinc of t was, remember, just a pulse in the frequency domain with amplitude 1, right? So from that I know that the integral is equal to 1. So sinc would have worked. Or I could have used Gaussians, a properly scaled Gaussian which is used as a distribution, in which case you actually have to attach these coefficients to it, 1 over square root of 2 pi e to the negative t squared by 2. That would be a Gaussian with standard deviation equal to 1. Okay, but you can scale that. But anyhow, the area underneath is still 1. So these are all candidates for constructing a delta. How do I construct the delta from a function like this? I squeeze it from the sides and I let it pop up, right? In other words, I define g epsilon of t to be 1 over epsilon g of t by epsilon, right? By doing g of t by epsilon, and epsilon being a small number, I'm squishing this guy, right? I'm compressing from the sides, but then I'm letting it have a bigger amplitude, so the area underneath is still the same. Does that make sense? Okay? So this was one particular construction using this g we generated this g epsilon, but this general construction would have worked with any other function that gives you an area of 1. Okay? So let's first make that clear, because in some other books you may see the delta function constructed differently. There was nothing special to the pulse. It was one of many candidates. All right? Clear? Questions? All right. Okay. So now comes the critical moment. So how do we make sense of these two things? One, our first sin, and our second sin. So things that mathematically are not well defined, but that we used anyway. So distributions come to the rescue. Okay. So here's a definition. Given a so-called test function x, a distribution t operates on f to produce a number. Okay, so the distribution is not a function, really. It's an operation on a given function that spits out a number, assigns a number to each function. Okay, so that's how we define a distribution. And the resulting number we denote in this form. If that looks like an inner product that you've seen somewhere, just erase that from your memory. It's not an inner product. It's just a convenient notation. Okay? Well, actually, you can... Anyway, so assume it has nothing to do with inner products. Okay? So this sounds really bizarre, but really what's happening here is this, right? So if you're a mathematician trying to make sense of 2, right, what would you do? Delta is not really a function. It's doing something in an integral, and f0 comes out, right? Well, then you define delta to be a new object, not a function, but as a distribution that does something to a function f and spits out a number, which in the case of the delta is the number f of 0. Okay? So delta is really going to be defined as a distribution rather than a function, which it is not. All right? So that's the source of this theory. Will be a little more concrete than this general definition. So what we will do is we'll define distributions that are induced or defined by a regular function, a well-defined function. Okay? Define distribution induced by function, let's say g, by function g as t sub g. The sub indicates that this distribution t was somehow defined by a function g, and I'll tell you how we are doing that right now, in the following way. Integrate g of t with x of t from negative infinity to infinity. Okay? So these test functions x are just functions. You know, we choose them from a class that are known to have well integrability properties. So they obey all the, whatever context we use them in, they satisfy integrability. Okay? So that is basically a definition of a distribution when the distribution induced by a function g. All right? If you are more ambitious and want complex numbers, you can put a star here and that still works. Okay? So this definition has two immediate properties. First, just following from this definition, we can conclude that I can take the distribution induced by the sum of two functions, g1 and g2, and guess what this would look like looking at the expression here. Can I write it in terms of t, the distribution induced by g1 and x, and distribution induced by g2? How will it be related? It's the sum, right? Because the g that you see here will be g1 plus g2, so you split the integral into two parts. Okay? So that's an immediate property. The second property is that if I apply Tg to not x but a coefficient alpha times x, what comes out is alpha Tgx. If I apply alpha Tg to x, because g was the one that got starred, it would be alpha star Tgx. All right, anyway, so these are some of the basic properties, okay? But so where am I going with this? So now remember the g epsilon that I used to define my delta function, right? If I use the distribution defined by, induced by Tg epsilon, and apply it to a test function, what would that give me? It would give me the integral of g epsilon, which is 1 over epsilon, g of t by epsilon, right? X of t dt. Okay? And then if I take the limit of this, so what is this doing? What is the distribution doing? It's multiplying the test function x with a g scale g, and it assigns the resulting integral as the result of the operation, right? Now, if I think of the limit of this, okay, if I define delta as the limit as epsilon goes to 0 of the distribution defined by g epsilon, okay, then this is going to be a reasonable definition, because we are not talking about functions. G epsilon doesn't have a limit as a function, but I can define it as a limit of this family of distributions. Okay, so this is this delta definition as a distribution makes sense of this thing here, because that really the left hand side is not a function, right? How does the delta become a function? It really isn't. The proper way of doing it, if you want it to be accurate, would be to define this as a distribution in this form. And as a result of this limit, you can also conclude that delta acting on a test function would give you a result of this integral that's a limit as epsilon goes to 0. And that will actually give you x of 0. Okay? And that's really what we wanted from this delta, right? So that was the property 2 that sort of didn't make sense because we were integrating against a function that is not really a function. So, but if we define delta as a distribution as I did, then 2 simply reads as distribution delta acting on x, spitting out x of 0. Okay? So within this theory of distributions, within this definition of distributions, we can actually make sense of the delta. Okay? We can also this is the last page I'm going to write, and I'll let you free for a short break. We can also generalize the notion of a Fourier transform without relying on the existence of that integral. Okay? Again, using distributions. So, suppose, okay, I will not give you the conditions, I'll just write something shorter. So, define the Fourier transform of a distribution T as follows. I'm going to use the script f attached to T to mean the Fourier transform of the distribution T. And the definition of the Fourier transform is as follows. You apply it to the Fourier transform of a test function, and the test functions will be ones that have well-defined Fourier transforms in the classical sense. Okay? And the distribution will have a Fourier transform defined through this equation, 2 pi times T acting on little x for test function little x and its Fourier transform big X. Okay? And those test functions are assumed to come from a class that converts so fast that their Fourier transforms exist in the standard sense, and so these operations are well defined. Okay? Without further ado, I'll just give you one example that is something that we already discussed, right? We talked about the Fourier transform of 1 being 2 pi delta omega, right? We sort of justified it, but the true justification comes from this definition of the Fourier transform. Really, it's this transform that I just highlighted that you're applying to 1 because the classical definition is not applicable. Okay? So how do I justify what I just wrote in terms of the generalized definition above, right? So what does that even mean, right? So we are asking for, if you think about the Fourier transform of the distribution induced by 1, okay? So basically, by writing this, we've claimed in our new language that the Fourier transform of the distribution induced by 1 is 2 pi delta, right? Why is that true? Well, just apply the definition. If T1 applied to x means what? It's the integral of ft1 with x, but we'll come back to it. Let's look at the right-hand side, right? 2 pi t1 in this case, the distribution induced by the function 1 of x. I know what that is, right? What is this? Here's the definition. Distribution induced by a function g acting on test function x is this, right? So just apply that here. G is 1. So that means equal to integral of 1 times x of t dt, right? So 1 changes nothing. You just get negative infinity to infinity x of t dt, right? So if you believe that if the Fourier transform of this distribution is 2 pi delta, then the left-hand side here is 2 pi delta acting on x of omega, right? And what would that give us? By definition, delta is a distribution. How does it act on a function? It grabs the function, takes its value at 0, spits it out as the answer, right? So that's the definition of the distribution delta. So that's going to give us 2 pi x 0, right? So the left-hand side gives me this. The right-hand side gives me that. Are they, in fact, the same? By what property? I guess it's just the definition of Fourier transform, standard Fourier transform, when the frequency omega is 0, because you multiply it with e to the negative j omega t, so that gives you the integral, right? So remember, the test functions little x here are things for which the Fourier transform in the classical sense exists. So we know this connection does exist, right? So therefore, what we've shown is that, you know, what we wrote somewhat loosely as this can be interpreted more rigorously in the sense of distributions. I don't expect you to follow all of this, but I want you to be aware of the issues, so what the convergence issues and how people get around them. So for our purposes, writing this as is perfectly fine. Okay? As an operational thing, it's fine, right? But do know that, you know, there are some convergence issues that a mathematician would quibble with, and they have, and they've developed the theory called distributions that actually deals with it. So from now on, I will be doing these things with a clear conscience. At least I told you how those things are justified. Okay? and the exam will cover this in great detail. Just kidding. No, none of this in the exam. This was just a glimpse of what it takes to make the Fourier transform rigorous for functions involving deltas and things that don't converge. Okay, sort of makes sense. That's good enough for me. All right? Okay, so take a break, 5 minutes, and then we start a new chapter, literally. Fourier transform known as DTFT. Okay, there are a lot of Fourier stuff. Okay, so this is there's CTFT, which is what we discussed, continuous time Fourier transform, and now comes the discrete time version of that, DTFT. There is also DFT. Let's not talk about that. It's not a big deal. The DFT is actually really simple. We'll talk about that when the time comes. Just ignore it for now. Okay, but just know that DTFT and DFT are different things. They are not the same things. Okay, what we are talking about now is DTFT, not the same thing as DFT, and definitely not the same thing as FFT. But FFT is really the same thing, although they are, FFT is an algorithm to do DFT computations quickly. Okay, in that sense, I can say the same, but one is algorithm, the other is the definition. So they are not technically the same. So let's not go into that. Okay, but before the exam, you won't see DFT. Okay, so you can relax, and even when you see it, you'll find it very manageable, and we'll see some connections to DTFT. Okay, so as far as the exam is concerned, Fourier series, continuous and discrete, Fourier transform, continuous and discrete, CTFT, DTFT, that's it, all right? And of course, whatever we discussed about LTI systems, convolution, right? That's all. All right, nothing to panic about. All right, so this is the definition of the Fourier transform at the top. And below, you're asked to compare it to the CTFT, and you will immediately see similarities. Looks very similar, except that, of course, one is continuous time, so it's an integral. The other is discrete time, so it's a summation, the usual difference. All right? So the next question is, where does that come from? Well, what is some motivation for this definition? Okay? As we did in the CTFT, whether you followed it or not, the motivation for the definition comes from Fourier series. Fourier series are perfectly applicable to periodic signals. What if it's not periodic? So then can you twist your eyes and see it as some kind of extension of as a limit of a periodic thing? So I am going to rely on my notes because I don't want to do almost identical things to what I did for CTFT. So to motivate the definition that I just showed you, you take an aperiodic signal x of n that looks like the one on the left, and you construct a periodic one by attaching it end to end. Okay, now it's periodic, so it's fully qualified to have its own Fourier series. And the Fourier series coefficients are defined as such. We put a tilde on the periodic version because tilde looks like a little wave, so it reminds us that it's kind of periodic. Okay? And then from the definition, we see that n times ak, if I carry this guy on the left to here, n times ak looks like this. And I can think of this here as, I can pretend this is a continuous variable, frequency variable omega, and then what I get here is the Fourier series coefficients ak being samples of that continuous function of omega, right? Samples taken at integer multiples of the fundamental frequency, which is 2 pi by n, right? As in our arguments in CTFT, as the period stretches to infinity, then we're talking about multiples of a very small fundamental frequency, omega naught 2 pi by n, which is going to 0, so that these samples would be very closely packed, right? So then, so if I plot x of omega like this, that means I'm taking, let's say this is omega equals 0, then I'm looking at the sample omega naught, 2 omega naught, etc. So I'm looking at these values, and I know those give rise to the Fourier series coefficients, right? So what I'm drawing here is n times I a k, right? Omega naught k. And of course, as n goes to infinity, omega naught is smaller and smaller, so these guys come together. So if you look at it from a distance, it almost looks like this continuous function. That's what motivates this definition of the Fourier transform. Okay? All right, and a derivation similar to that, or a justification similar to that, exists for the synthesis equation to reconstruct a signal from its Fourier transform. And that follows similar reasoning to CTFT as well. What we do, we did this there, I don't know if you remember. If you don't, compare the notes, you'll see similarities. So if I know the coefficients A sub k, I can construct my periodic signal from a Fourier series. But remember, in discrete time, Fourier series are, we only need finitely many of those sinusoidal things, right? We only need n of them, unlike continuous time where you may need infinitely many. So keep that in mind. So we are only looking at a finite sum here. And we know that these coefficients AK, which I hate, no. Anyway, so the coefficients AK are these guys, as we just discussed, right? So if I substitute that in, I can rearrange this finite sum in this form. So I divide and multiply it by 2 pi. The reason for doing this is because 2 pi over n now looks like the fundamental frequency. And then the summation I get looks like the definition of an integral. In fact, it coincides with how you would take the integral of this function over omega. Okay? So the one thing we have to note, one difference, the same thing was happening in continuous time case, but the one difference is that now this is a finite sum. We only sum n elements, capital N elements. So even though we are doing these stepwise things, spaced apart by omega naught, right? The number of those is increasing, of course, because omega naught is now smaller. But we still have n of those. At the end of the day, the summation is done over n terms. So that means what we converge to is an integral of period to pi, not an integral from negative infinity to infinity that we got in continuous time synthesis equations. Okay? Again, the reason is we have things of width omega naught 2 pi by n. Okay? And we have n of them. So when you multiply n and omega naught, you get 2 pi. Right? So the integration you're doing is over a fixed period. It's from 0 to 2 pi if you want. Okay? So that's another difference. But that gives us the synthesis equation. So what is important is to remember the analysis equation, which we already talked about, and the synthesis equation, which is motivated by this discussion. All right? They are analogous to the continuous time Fourier transform, the differences being an obvious one for the analysis equation. It's summation in terms of instead of integral. Another difference in discrete time is in the synthesis equation. You're not integrating x over the whole frequency variables from negative infinity to infinity. It's only over a period of 2 pi. The reason comes from an important property of the discrete time Fourier transform. It is periodic. Okay? Why is it periodic? Let's go to the notes. If I look at this definition, and if I put x of e to the j omega plus 2 pi, let's see what happens. I'm going to get the sum over n, x of n, e to the negative j omega plus 2 pi n, right? So split this as e to the negative j omega n, e to the negative j 2 pi n. N is an integer. So you're talking about a complex number whose angle, the angle that it makes with the real axis, is an integer multiple of 2 pi, which is really 0, right? So that means this number is 1 for any integer n. Okay? So therefore this term drops out, and what is left is the same thing that we defined as the Fourier transform. Okay? So therefore, the discrete time Fourier transform is periodic. Is periodic in omega with period equal to 2 pi. And it's a result of that, as a result of that the synthesis equation is an integral over 2 pi. So it's 1 over 2 pi. Integrate over any period that you like that lasts 2 pi units in omega. And the product the omega will give you x of n. Okay, so that's the synthesis equation. And that's the difference from continuous time. So there is no reason not to call this x of omega. I could have done that. Okay, but we've come to the point where we've used this for continuous time Fourier transforms, right? And when we use this, if you use the same notation for DTFT, you can still discern them, knowing where it came from. But the reason we use this is to remind us right away that this came from a discrete time signal. It's the DTFT, not CFT. Okay, but at the end of the day, it really is a function of the variable omega, right? So I could have just used this. So going forward, whenever these things arise, if it's continuous time Fourier transform, we're going to use x of j omega, because there it always appears multiplied with j. And in discrete time, we will call it x of e to the j omega. All right? So this will also remind you that this is a periodic function of omega. All right, so that's the DTFT. Let's look at some examples and make it a little more concrete. Oh, and then remember the theorem that we started with? The convergence condition for CTFT? Convergence of CTFT guaranteed if, that was a sufficient condition, if x of t integral dt existed. Can you think of a similar rule for DTFT? Very simple pattern matching. You can do it, I know. What would be some analogous result to this absolute integrability? Absolute summability. So you can sum x of n over n, and that sum converges. Okay, so that again is a sufficient condition for the existence of the Fourier transform in discrete time. Okay, similar extensions exist to using deltas, etc. So I'm not going to repeat those. I knew I could only do that once, and I did it already for CTFT. So similar things work for DTFT as well. Okay, let's look at examples. So the first example is an exponential function, x of n. So this is going to mimic sort of this example from CTFT. Remember, we had e to the at, u of t. A was positive, so this is a nicely convergent thing, and this condition of absolute integrability works, right? Because an exponential decaying thing will be absolutely integrable, right? And that gave us, how many people remember here the Fourier transform of that? A plus j omega, right? Okay, so we're now looking for an analog of that in discrete time. So think of a function that decays exponentially, and you don't have to go to e, exponential function to do that, because now you're talking about functions of an integer. Give me a function of discrete n, give me a sequence x of n, right, that goes to 0 exponentially almost the same way that e to the negative at does. Okay, how about 1 over 2 to the n? What does that look like? Let's multiply it with u of n so that we're not talking about negative values of n. So at n equal to 0, it's going to be 1/2. At n equal to 1, at n equal to 0, it's 1. At n equal to 1, it's 1/2, and then 1/4, 1/8, and quickly goes to 0, right? So, in fact, we can make that more general. We can just say a to the n times u of n. And it will, again, if a is smaller than 1, right, it will converge like that. What happens if a is bigger than 1? Or what happens if a is 1? Stays the same. That's like little a being 0 in the continuous time example, right? If a is bigger than 1, this is then exploding exponentially. If it's 2, then it goes like 4, 8, 16, etc., blows up really quick. So similar to this condition here, we're going to limit a to be less than 1 so that we have exponential drop, therefore integrability, and the DTFT then will exist. So let's do the sum required for finding the Fourier transform. It is the sum from negative infinity to infinity x of n times e to the negative j omega n, right? Now, the signal is 0 before time equal to 0, so we don't need to run from negative infinity. We just have to run from 0 to infinity, right? And x of n is a to the n. I multiply it with e to the negative j omega n and do this sum. So I've done nothing but the definition, apply the definition of the Fourier transform to this signal. Okay, so I don't know if you ever discussed this. I think in one of the first lectures I did. So what this looks like is a sum 0 to infinity of I don't want to use the letter. What is a good letter? Some letter that doesn't offend you. So, but doesn't look like the usual x, y. Z. Good. Z is good. Z to the n. Okay, where z is a e to the negative j omega. Do you agree? Yes? Okay. So that looks like 1 plus z squared, etc., right? And turns out if z as a complex number has absolute value less than 1, this series converges. You know to what? 1 over 1 minus z. No, just 1 minus z, right? Yeah. For how many of you this makes, no, it does not ring any bells? So you've seen this? I guess I asked the wrong question. How many of you think this is obvious? Okay, so there's still a complement of this set. So, okay, so, okay, I think we did something like this before, but let's just remember that. If I take something like this, z to the n, right? This is the same as 1 minus z to the n plus 1 divided 1 minus z. If z is less than 1, therefore you have no division by 0, right? Why is that true? Well, verify this by multiplying both sides with 1 minus z. If I multiply the left-hand side with 1 minus z, first multiply it by 1, so it's the same thing, right? Z to the n, right? And then multiply it with negative z. So you're going to get negative z. I'm going to shift it to the right so you see the cancellation. Negative z squared, negative z to the n. That came from zn minus 1 here. And then finally negative zn plus 1. So all of these guys in the middle cancel, and we are left with 1 minus zn plus 1. So that's how this is justified, right? Now take n to infinity. Then the left-hand side of this is going to this sum from k0 to infinity of z to the k, right? And the right-hand side is going to 1 over 1 minus z, because this term here, z being smaller than 1, its powers, as it increases, it's converging to 0, right? So that's where this comes from. So if we just apply this here, we get the final result, which may look a little messy, but it is what it is. So 1 over 1 minus z. And remembering that z is this, we just substitute it here, e to negative j omega, again, with the condition that is smaller than 1. Okay? If it were 1 at omega equal to 0, this wouldn't be even defined. Okay? And in fact, again, if a were 1, the sum that's needed in the DTFT definition does not even converge. We would have to use deltas to make sense of the Fourier transform, as we did in the first hour. Okay? Questions? So this does not look pretty, perhaps, to you because it's complex. What kind of signals give us Fourier transforms that are real and therefore look nice and you can plot them? You need some kind of symmetry about t equal to 0, right? So you did that in the discussion on Friday for the exponential function. You had a two-sided exponent, right, which I used as one of my 5 Fourier transform pairs at the very beginning of this lecture. So we could do the same thing for this discrete one. So I'm going to make that my example 2. Example 2. So we'll define x to be what on earth is this? Oh, yeah, we'll define that to be a to the n if n is positive, and a to the negative n if n is negative, and that makes it symmetric. As a result of this definition, x of negative n is the same as x of n. So it looks like the Bay Bridge a little bit. So, you know, you have, it's symmetric about n equal to 0, right? So it dives down on both sides. Okay, so because it's symmetric, I haven't really explicitly proven this, but we saw analogous results in the CTFT. Even symmetry of the function with respect to t equal to 0 gives us a real valued Fourier transform, which is nice. So if we do that here, we can evaluate this sum and calculate the Fourier transform. But really, it's easier to decompose this example into a function like the one in the previous example. So I'm going to call this x1, if that doesn't bother you. I'm going to call it x1, 1 for example 1, okay? So because I know that my function for n, 0, and positive values looks like the previous example, so it sounds like unnecessary work to repeat the Fourier transform definition. So x of n could be written as x1 of n, but x1 doesn't have the left-hand side, right? So how would I create that? I should add something to this that will generate the left-hand side. What might that be? x1 of minus n, because that will be the opposite. The same thing, the mirror image with respect to n. But be careful now. You may have done some double counting. For at n equal to 0, you have 1 really, the signal is 1, whereas when I add them, they are both 1 at n equal to 0, so it gives us 1. So we would have to subtract from this a, what? Not 1. Subtract from the signal 1 only when n equal to 0. What's a good function that does that? Delta. And discrete time in discrete time, delta is a good guy. It's a real function. I mean, it's a real thing. It's not this explosive thing that requires a tremendous amount of theory to justify, right? In fact, why didn't I make that example 1? Or let's make that example 0 here in a little corner, because it's not even an example. I mean, it doesn't deserve a number that's different than 0. If x of n is delta of n, what is x of omega? E to the j omega. It's sum of delta of n e to the negative j omega n from n negative infinity to infinity. But that sum does nothing, really, because delta is always 0 except when n equal to 0. It really is not a sum. It is just delta of 0 e to the 0. And delta of 0 is 1, right? So this was a more tedious thing in the continuous time. We use this delta, which really is a distribution but wants to be a function, right? And then we argued in funny ways that it actually gives us a Fourier transform that's flat equal to 1. In discrete time, this is totally legit. I didn't break any rules. I didn't offend any mathematician. I just, calculated the sum. It is that, okay? All right, so then I can write delta of n. So the rest is fairly straightforward. I already know this gave me what? What was it? 1 over 1 minus a, what was it? A e to the minus j omega, right? Okay. Okay. So, question mark. But tell me that. We just studied this. It is 1. Okay. So the other one is basically going to follow. I'm just going to give you a preview. When we talk about the properties, we will see the following property. If x of n gives you, okay, to be done, TBD, later, but good to see a preview, then we will have motivation then. If x of n gives me Fourier transform x e to the j omega, x of negative n gives me x of e to the negative j omega. Fairly easy to remember and very easy to prove too, so I wouldn't even probably prove it. You should do this on your own. So therefore, I don't need to do any more work here. I just have to take this expression, flip the sign of omega, and that will be the Fourier transform of the second piece. So 1 over 1 minus a e to the positive j omega. And the Fourier transform has the additivity, the superposition property. It's linearity property. So I can actually add the Fourier transforms. So this is the answer. This is the Fourier transform of x. Okay? Now you might think, didn't we make x pretty nice and symmetric? So this x of e to the j omega should not really be complex, right? So it is not complex only because we didn't show it's complex. You can actually simplify this to make it complex. Okay? The usual thing where you multiply the denominators, make them equal and all that stuff will do it for you. If you really want me to do it, I'll do it, but you probably don't. Okay, I'll do it. Wait. This is big X. Yeah, so that's what I said. So when I do discrete Fourier transforms, of course I can call this X, right? Who cares? I mean, it's a function of omega, right? I said when I'm doing DTFT, I'm going to use this weird notation just to remind you that this is the DTFT. You don't have to, but So, yeah. Oh, yeah. What? Wait. What? It is not the same thing, therefore it wouldn't be the same x. Okay, don't get me into this. So I could just call this x. Okay, so when we define Fourier transforms, we will just use the argument e to the j omega, although it makes it eventually a function of omega, right? I can call it x tilde of omega, right? But if you want to use x of omega, that's totally fine for me. Okay? I just want to somehow differentiate it. Like I said last time, when we talk about frequency responses, we had h of e to the j omega. You didn't complain then, right? And then h of j omega, right? So that is equally nonsense. I mean, why is it not just h of omega? But it was just something to remind you. Okay? If you accept that, we'll be okay with this. All right. All right, so what I was doing here is 1 over 1 minus a e to the positive j omega and minus 1. So do the usual high school thing, e to the j omega plus 1 minus a e to the negative j omega. These are the first two terms. And what is the product of these two? So 1 minus a e to the negative j omega plus e to the positive j omega, and then the product a squared times e to the negative j omega times e to the positive j omega. So those cancel. So I get a clean a squared. And this also is a clean term, actually. Right? What is it? Clean meaning real, I guess. 2 times cosine omega. And the numerator, so I'm only dealing with these two terms so far, okay? And the numerator is what? 1 minus 2a cosine omega, right? Wait. 2? 2, yes. 2 minus 2a. Or 2 times, yeah, okay, 2 minus 2a. 2 minus 2a, all right, 2 is good. Divided by 1 minus 2a cosine omega plus a squared, almost the end of the story. Now we have to subtract 1 from this. So I think that 2 will become 1. Cosine omegas will cancel. That's nice. And then we're going to have a negative a squared here. I don't know if I'm doing this right, but I think something like this comes out. And as expected, this is now real value, because symmetric functions with respect to t equal to 0 should give us symmetric things. All right. In fact, that matches my notes. For once, I didn't make any errors. Okay. So, what else? Okay, so things I don't want to do here, I'm just going to do notes. I spent a lot of time on these notes, so I might as well use them. So this is what I just discussed. Now here's something that also resembles what we did in discrete continuous time. So this is a pulse of length 2 and 1 plus 1. Okay, so the signal that you see on the left. So doing the Fourier transform is not so hard in this case because the summation only goes from negative n1 to n1. What you're adding is really 1 times e to the negative j omega. So it's fairly straightforward. And you can show that this sum can be written as sign by sign with different arguments. Didn't we do this somewhere? We did this somewhere when we did this in a pretty lengthy way. You know, the derivation was, I did it here, and then somebody said, oh, it's signed by sign something, so it bevels in the middle. So I'm pretty sure we did this. That's probably why I don't have it in the notes. Oh, yes, I told you I'll do it once, and the next time I'll refer you back to it. Yes? Yeah, DTFT is a continuous function of omega. Okay? So that's the interesting thing about DTFT. So even though the signal itself is discrete time, its Fourier transform is a continuous function of omega. It's a continuous frequency variable. When we go to this guy, DFT, that's no longer the case. The Fourier transform itself is discrete. But again, don't worry about that yet. Right? So, okay, so if you believe this expression, again, I'll refer to whatever lecture that was in, because I told you then that I'm not going to do it again. So that's what I'm practicing right now. In fact, I said derive this as an exercise. Which lecture? Note to self. Okay. All right. Okay, so then the Fourier transform looks like this. Okay. It's kind of like the sinc function, right? Because in continuous time, the pulse in time domain gave us a sinc in the frequency domain. This is very similar, but this is not the good old sinc, because remember, the dtft has to be periodic in omega with period 2 pi. So this is a periodic sinc in a sense, right? So the definition is not signed by, sinc was defined as sine pi t by pi t, right? This one is sine something omega by sine omega. Okay, so that makes it periodic inherently. Okay, so think of it as a periodic version of the sinc, but in DTFT, of course, we don't have to plot these from negative infinity to infinity. Knowing that it's periodic with period 2 pi, we are content just looking at the figures, plots from 0 to 2 pi or negative pi to pi, right? So that's more than enough. Okay, so you see this sort of symmetry compared to the continuous time pulse, yes? Some kind of sinc still, but a periodic one. Okay, next. We are now going backwards. So when we talked about x of n, delta of n, giving us a Fourier transform x equal to 1, there was nothing wrong there. We didn't need any special care because delta is a well-defined function. The sum converges and everything. There's nothing wrong, right? But now things are getting a little more complicated because we're going to go backwards from the delta function in the frequency domain. Now it's because omega is a continuous variable like you just asked, right? Delta of omega is the real Dirac that we just worried about and defined it as a distribution. It's the more complicated delta, not the simple discrete time delta, right? So, but if you apply the synthesis equation, you're going to get, because you're integrating over a period of 2 pi, you'll just get x of n equal to 1 over 2 pi, okay? So it comes from this here, from this equation. So because I put delta of omega for my Fourier transform, this will spit out the value of at omega 0, which is 1 over 2 pi, right? So from the linearity property, so that means if x of n is 1 over 2 pi for all n, it gives you delta of omega as the Fourier transform. Therefore, 1, x of n equal to 1, would give you 2 pi times delta of omega, just by the regular scaling properties. But be careful here, because what I said here is when omega is between negative pi and pi, because I know these Fourier transforms are periodic, right? I can't just have the Fourier transform of a discrete time signal be delta of omega and nothing else. Delta of omega is not periodic, right? The only thing that would make sense is a delta that repeats itself every 2 pi. Okay, so that's why I said let x be defined this way in this interval. But really what that means is x has this form. It's a train of impulses with period 2 pi, right? Anyhow, but you do the integration in the synthesis equation over a period, so the copies don't bother you, and you get a constant, okay? Similarly, this is very similar to what we just did in the first hour for continuous time Fourier transforms. You can show that, I hate this. So you can show that e to the j omega 0 n goes with this Fourier transform, right? So you have an impulse located at omega 0, and of course, multiples of 2 pi, continuous periodically. So this resembles what we did in continuous time. And of course, again, if you take omega naught to be 0, the function is 1, and this is an impulse centered at 0, which recovers the previous example. So doing this, we can define Fourier transform for periodic signals the same way we did for the continuous time case. So the Fourier series coefficients get multiplied by 2 pi, and then they become deltas. All right, where am I? Okay, so the Fourier series coefficients, the Fourier transform of a periodic signal then will look like this in the frequency domain. And we don't need to continue, of course, because 0 to 2 pi will be good enough. Okay, so Fourier transforms have the usual properties. Time shift is one of them. One of the easiest to show too. So if I apply the Fourier transform definition to this, I'm basically doing x n minus n0 e to the negative j omega n and summing this over all n, right? Now what I can do is I can define this guy, not that, sorry. The argument n minus n0 to be m. And therefore n becomes m plus n0. And I can shift, I can do the summation over m now, nothing changes. So this is m, negative infinity to infinity, x of m, e to the negative j omega m, and e to the negative j omega n naught. Okay? This second term does not depend on m, so I can split it. I can take it out of the summation, and what remains in the summation is really the Fourier transform x itself. So that's where this result comes from. If I shift the signal in time, that's the same as multiplying the Fourier transform with e to the negative j omega n 0. Just like in the continuous time case, same property. And that also means shifting a signal in time doesn't change the magnitude of the Fourier transform. It only adds phase to it. All right, so next property, frequency shift. That's sort of dual. So if I shift this Fourier transform by omega naught, that's the same as multiplying the time domain signal with the sign e to the j omega 0 n. That's called the modulation property or the frequency shift property. We did the same thing in continuous time, and we had a nice example for that. Do you remember what the example was? You multiply with a signal with a sinusoidal, and then its spectrum shifts. What was the example? Amplitude modulation, AM, radio, right? You modulate the signal, multiply it with a sinusoidal, that moves it in the spectrum to its allocated spot. Okay? So it's the same type of thing. A special case of this is taking omega naught to be pi. If I take omega naught to be pi, then this is e to the j pi n. But what is e to the j pi? Complex number that makes 180 degrees with the positive real line is, I guess from your view it's this way, gives me negative 1, right? So really then that amounts to multiplying the signal x of n with negative 1 to the n. So what you are doing to your signal is you're taking the values of your signal. If n is even, you leave it alone. If n is odd, you multiply it with negative 1. Okay? And the result of that is to shift the spectrum by pi. You take the Fourier transform, slide it by pi. But remember, the Fourier transform is periodic with 2 pi. So what you've really done is you took whatever existed around omega 0, shifted it around omega pi. Right? So if this is a signal like most other signals where the spectrum concentrates around omega 0 and decays as omega reaches the high discrete frequency, which is pi, right? So if it's the usual spectrum where you have that kind of property, so let's say x of n gave you an x of omega that looked like the usual thing where things are large around omega 0, and then by the time they get to pi, they are pretty small, and then they go up again, because going beyond pi is again slowing down the frequencies, and at 2 pi you're back where you started, right? And the rest is periodic. We know that about DTFT, right? So really what we care about in the DTFT, first of all, 0 to 2 pi, no more than that is necessary because we have periodicity. But we will see shortly that also, 0 to pi is enough because the other part is basically a complex conjugate, some mirror image of that, okay? So x of n gave me this x of e to the j omega, right? If I multiply this with -1 to power n, that shifts it by pi. So now I get x of e to the j omega minus pi. So what that does is it brings what was around omega 0 to around omega equal pi. Okay? So what happened? So low frequency content got shifted to the highest frequency, right? So if this was a well-behaved signal, slowly moving signal where the spectrum would be concentrated around omega 0, now it's a very jumpy signal because of this multiplication. And that kind of shifted the spectrum to concentrate it around pi, which is the highest frequency, right? That kind of makes sense because if it was a slowly moving function like this, now it's anything but, right? It's jumping all over the place. And it's a really high frequency signal. So that shift kind of makes sense because pi is the high frequency. Okay, let's stop here and we'll take it from here next time. All right, I think this is good enough for today.